Oh boy, do we have a long intro? This is like, I don't know, 10 paragraphs, 10 paragraphs long. But I'm gonna see how far we can go, and let's just go. So a neutron star is a collapsed core of a massive supergiant star. Supergiant star seems like it's just a massive freaking star. Supergiants are among the most massive and most luminous stars. Collapsed core. Okay, so they can so stars I think like have an evolutionary process and they can at some point collapse or implode or explode. So I guess if they implode, if the core collapses, we get a neutron star. But I thought we get black holes. So I don't know. Okay, so let's keep reading. It results from the supernova explosion of a massive star, combined with gravitational collapse. So we have explosion and implosion that compresses the core past white dwarf star density to that of atomic atomic nuclei? What? To that of atomic nuclei? I'm confused. What does that even mean? So it's compressed past a white dwarf density to that of atomic nuclei. It just says atomic. Like I'm imagining the size of an atomic nuclei. Like the whole thing is the size of an atomic nuclei. That seems really small. I must be missing something. But let's keep reading. Surpassed only by black holes, neutron stars are the second smallest and densest known class of stellar objects. Okay, so if this is an atomic nuclei, how freaking small is a black hole's size? Okay, yeah, the universe is insane. Universe is insane. Okay. Neutron stars have a radius on the order of 10 kilometers. So it's not an atomic nuclei. I don't know. I don't get the sense. If somebody in the comments wants to help me understand this, please do. All right. Surpassed only by black holes. Let's keep reading. Okay, so neutron stars have a radius on the order of 10 kilometers and a mass of about 1.4 m dot. Don't know what that means. So 10 kilometers and a mass of, maybe that's like the solar masses. Maybe that's what that is. Stars that collapse into neutron stars have a total mass of between 10 to 25 solar masses. Got it. Once formed, or possibly more for those that are especially rich in elements heavier than hydrogen and helium. Once formed, okay, before that, let's have a look at some cool pictures. So, central neutron star at the heart of the Crab Nebula. So, maybe it's this or that or this, I don't know. But there's something there that's a neutron star. Radiation from the rapidly spinning pulsar. I don't know what that is. Okay. Diagram. Massive star. Inner core. Inner core implodes under gravity. Gravity smashes electrons and protons together, forming neutrons and releasing a shower of neutrinos. Outer layers slosh violently from standing accretion, shock, and stability. Outer layer implodes and collapses into the inner core at 25% the speed of light. So it goes into it, and we just have... So we used to have this big old gray thing, and now we have this tiny white thing. And then outer layers bounce off the dense core, creating a supernova. Resultant free core is a neutron star. So it's like the the core has collapsed into this white little ball, and then after it sheds kind of the remainder of the outer core, which kind of bounces off in a supernova, we're left with like a neutron star, which is slightly more or less dense than a black hole. So it's like the step up. So we have black holes, and then we have neutron stars. All right, we've got a lot more to read here. I don't know if I'm going to finish it today. Once formed, neutron stars no longer actively generate heat. What? Just like dense billiard balls, and they just start cooling. But they may still evolve further through collisions or accretion. Most of the basic models of these objects imply that they are composed almost entirely of neutrons. Holy shit. Neutrons are... Wait, neutron is like a part of an atom. Like an atom has neutrons, protons, and electrons. So it's just neutrons? That's insane. As the extreme pressure causes the electrons and protons present in normal matter to combine into additional neutrons. Holy shit. The protons and electrons just turn into neutrons? Wow. These stars are partially supported against further collapse by neutron degeneracy pressure, just as white dwarfs are supported against collapse by electron degeneracy pressure. However, this is not itself sufficient to hold up an object beyond 0.7 solar masses. And repulsive nuclear forces increasingly contribute to the supporting more massive neutron stars if the remnant stars has a massive mass exceeding the Tolman-Oppenheimer-Volkoff limit, which ranges from 2.2 to 2.9 solar masses. The combination of degeneracy, pressure, and nuclear forces is insufficient to support the neutron star, causing it to collapse and form a black hole. The most massive neutron star detected so far is that one called PS 30952 and has that mass. Okay, folks, we have a lot more in this. There's no way I'm gonna get through this because like there's just so much new stuff that I have no idea. So I might just call this a part 1. And that's it for neutron stars for right now.